My name is Manish Gupta, and in this video, I'm going to talk about Stable Diffusion 3, which is based on this MM-DiT architecture. It's an image generation model which uses rectified flow transformers for high-resolution image synthesis. It is also an ICML 2024 best paper, awarded ICML 24 best paper. Okay, so let's get started. Let's just start with its capabilities. So what can Stable Diffusion 3 based on this MM-DiT architecture do? So, well, it's an image generation model, as I mentioned, and it is better than Stable Diffusion XL, a Stable Diffusion XL Turbo, PixArt Alpha, and DALI 3 models. Okay. These models are, of course, also available on Hugging Face as Stable Diffusion 3, and you can basically download and use them. They can generate, as you can see across so many pictures, high resolution samples from 8 billion parameter model. So it's an 8 billion parameter model, gives very high resolution samples, can lead to very good typography. So the spelling mistakes in the text that is printed is very small. So you can basically ask it to essentially generate a particular text in the image, precise prompt following. So if you basically say it should be a pen and ink drawing, it basically leads to pen and ink drawing. You could basically tell it tilt, shift, aerial photo, and so on. So basically it shows very good prompt following and spatial reasoning. So you could basically say, certain things should be on top of something else and so on, above a farm. So a spaceship above a farm. So you can see those spatial reasoning as well nicely. Attention to fine details and high quality image across a wide variety of styles. You can see several styles. Here is a pen and ink image. Here is basically some sort of a cartoon character and high contrast, dark high contrast render and so on. Okay. So that's that. So Stable Diffusion 3 is a state-of-the-art image generation model. Now, let me get into a little technical details about how is Stable Diffusion 3 trained and how does it work. Well, diffusion models have been very popular for image generation in general. And the way diffusion models work, I've basically made a video long back about how diffusion models work, but in short, they create images from noise by inverting the forward paths of data towards noise. So basically, you start from data and you try to add noise step by step over several iterations until you get an extremely noisy output, right? And that's basically called as forward path. And then, in the reverse process is basically start from noise and you try to generate a good image step by step in that sense. Okay. Now, these diffusion models to generate images are iterative and compute intensive. They actually take very long to be able to generate images at inference time. Okay. So now the choice of the the forward process is the process of taking data, that is images, and converting it to noise. The reverse process is the reverse of it, which is basically taking noise and then actually generating a real world image sample. Okay. Now the choice of the forward process also influences the learn backward process or the reverse process, and thus the sampling efficiency. Okay, so if you choose the forward process properly, you will basically get a very efficient, inference time generation. Okay. So now the way this iterative process works, it basically can take a curved path and therefore can be super slow. A simple way of doing this is to take a straight path, which is less prone to error accumulation and is also efficient. It's faster also. Okay. So rectified flow is one way of actually taking a straight path approach rather than the diffusion model approach to image generation. Okay. Rectified flow basically says, let me connect data and noise in a straight line. So essentially, it basically says that, yes, I'm going to move closer to data as I start from the noise, but here I'm going to move in a straight line, making it super efficient and therefore less error prone as well. Okay. So now, broadly, whether it is a diffusion model or rectified flow, generative models actually what they try to do is to define a mapping between samples x1, noisy samples x1, from a noise distribution p1, and the mapping between x1 and x0, where x1 is a noisy sample from a distribution p1 and x0 is a real world image sample from distribution p0. So now to move from x1 to x0 is what we want to learn, right? So essentially, and these rectified flow models essentially come up with the straight line flow trajectories. Okay. So there are multiple flow trajectories, although, right? So essentially there is this noisy sample P0 and you want to, or rather noisy sample X1, and you want to move from that to a noiseless version X0. Okay. Now, a way to move is basically rectified flow, but there are two other ways of moving on these flow trajectories from noise to data or data to noise in that sense. Okay. So a rectified flow basically says that, hey, I'll move on a line. So as time t passes by, I'm basically going to, so this is basically the forward process. I'm basically going to, as time t passes by, right? I'm going to move closer and closer to noise and further away from x0, which is the real world image sample. Epsilon is the noise that I'm adding. Okay. So it's a Gaussian noise. It's a white noise that I'm adding. Over iterations, I'm going to add more and more noise so as to basically have this forward process in a straight line manner. EDM is a different kinds. It's x0 plus bt epsilon. So there is a way in which bt is defined in the paper. I'm not going to go into those mathematical details. Cosine is yet another way where, as you see, it's basically the clean sample and the noise being added in a cos and a sine kind of a ratio. Okay. So, so more into this rectified flow. Of course, there are these other two ways of doing things also, and they compare with them as well. But more in rectified flow, the trajectory is uniform. The trajectory basically is defined by time t, right? So you start with the time t equal to 0, and you basically take several steps to get to move from data to noise or noise to data, the other way around process. And the way this is done is time is normalized. Therefore, on the trajectory, you could uniformly sample time steps in 0 to 1. So if you basically have a line, you cut it down into equal segments and say, oh, I have 50 samples. And basically, I'll slowly one by one move from data to noise or noise to data. Okay. However, the resulting prediction target, which is basically this epsilon minus x0, is more difficult for time points in the middle of 0 to 1. Okay. So the idea is that as you're learning this, right, you're trying to predict that, hey, if I add so much of noise, how will the sample look like? Okay. So predicting that is super simple, closer to the noise or closer to the original image, those particular time points. In the middle, it's much more difficult. So it's easier, closer to the to the in noise, because at time t equal to 0, all you have is noise, right? So essentially, the optimal prediction is just the mean of the noise prediction noise distribution. Okay. Closer to the original image sample, also it is easier to predict what is optimal, because just the mean of p0, which is basically mean of typical images, right? In the middle is where it is difficult. And therefore, rather than uniform sampling, you should sample more time points in the middle rather than actually having equally spread out time points. Okay. So therefore, you must give more weight to intermediate time steps by sampling them more frequently. And there are two ways of doing that sampling more frequently in the intermediate time steps: logit normal sampling and cosmap or cosine schedule based sampling. Okay. Again, I'll not really go into details about how this is done, but there are these two ways, and these two ways are the ones that basically make these rectified flow based trajectories possible for image generation, and that is what makes Stable Diffusion 3 the most awesomest model for generation. Okay. But that's just one step. So, diffusion models in earlier times used to basically use a unit as an architecture for reverse process. Okay. So they would basically use unit and several iterations over the unit architecture so as to generate images. However, over time, transformer models have proven to be really useful even for diffusion. Okay. And therefore, Stable Diffusion 3 basically uses MM-DiT architecture, the multimodal DIT architecture, diffusion transformer architecture, so as to generate images. Okay. So as I mentioned, of course, generation of images is going to be done starting from a noisy sample, and then you're going to denoise it step by step. And you're going to basically follow a logit normal sampling or cosmap sampling so as to define after how many time steps. I mean, how much from between noise and actual image you're going to sample. What is that sampling point? What is that operating point? However, in every step that you do, you're basically going to depend on a pass through this MM-DiT model. Okay. Now, what is this MM-DiT model? Well, it's a DIT model, diffusion transformer model. So it basically uses transformer for generating images. Okay. So let's basically see how it all works. Okay. Now, this is all done in a conditional way, in the sense that you basically don't generate images without any input. You basically have the image caption, text caption as the input, and you want to generate images following that text caption. Okay. So you have the text caption as the input, and you also have the noisy latent as the input. So remember, all of these generative models, basically they do generation in the latent space, and then they have variational autoencoders so as to basically take that generated latent and convert it to an actual full-blown image, right? So So the way this works is that this is the left side is the overall MM-DiT architecture, and in the middle is the overall MM-DiT architecture, and then a particular MM-DiT block, this one that you see, is full blown on the right side. Okay, so let's go over it step by step. You take the caption, you pass it through these three different text encoders. They're clip-based models, three different text encoders, and you see, I mean, you basically get some representations, some size representations. You could, of course, pool, and you can essentially get one-dimensional representation, but you could also do pooling in other ways, concatenation in other ways, so as to basically get larger sized text representations also. Okay. Now, whichever way you do this, you basically pass it through a linear layer or MLP, right, or multiple linear layers, so as to essentially get some activations here. You also pass it through a linear layer. You basically get some output here. Okay, so so that's that, right? The noisy latent that you have is basically of the same size as the image. So therefore, what you do is to find patches. Specifically in diffusion transformers, you take 2x2 patches. So remember, this is a diffusion image transformer kind of a model. So basically, you have to, of course, take the image and cut it down into patches, tiles, right? 2x2 tiles. Okay. You essentially pass them through a linear layer, add position embeddings to every tile, so as to essentially get X. Remember, X is the representation of the latent. So this is what you are going to update. Okay. So after one step through the MM-DiT, you will get an output, and your output is going to become the noisy latent for the next step in that senses. Okay. There is also a time step that needs to be encoded. So as time passes by, this time step increases. So time step is basically processed through a sinusoidal encoding, so as to get an embedding representation for the time step, and that's what you add and get this Y. So you have Y and you have C, right? So you have Y, you have C. Both are derived from the text if you think about it, right? So C is basically the label, the caption, and Y is also derived from the same caption, but more like a super highly pooled representation in that sense. Okay. Okay, so now this, so essentially the MM-DiT architecture prominently takes three inputs, this Y, this C, and this X. Of course, Y and C are derived from the caption in that senses. Okay. And then it's processed through D different MM-DiT blocks, as you see them here, D different MM-DiT blocks. We'll understand what happens in those blocks on the right side, but there are D different blocks. After all of those are done, you essentially pass them through these further layers. Modulation, we'll understand what modulation means. Modulation is basically modulated attention, okay, which will also you will see here, but you pass them to modulated attention layer, and then through a linear layer. Finally, whatever you get, the output that you get, you're going to unpatch it in the sense that you get those tiles and you stick them together to generate the output. This output is a latent output. You'll pass it to a variational decoder, so as to basically generate a high resolution image. Okay. Now, what happens in each of these MM-DiT blocks, right? So the following happens on the right side. Whatever you see is what happens in these MM-DiT blocks. Remember, to each MM-DiT block, you're passing three inputs: Y, C, and X. So here is your Y, here is your C, and here is your X at the top, right at the top. Okay. So in fact, these MM-DiT blocks basically they process these image and the text inputs separately in some ways. Okay. So as you see on the right side is on the left side is the text tower in that senses. On the right side, what you see is the image tower, right? So remember, your X is basically image, that is the latent image that has been processed. And on the left side is basically text. Okay. So of course, in between you see self-attention going on, or other, you should really think about it as cross-attention here, because it's image and here there is basically text also, but it's basically what is called as modulated self-attention, and we'll basically see how it all works. Okay. So you take Y, you basically pass it through some nonlinear, CLU, so some, ReLU kind of nonlinear activity. It's called CLU, okay, a different activation function. Pass it through a linear layer, and that basically gives you your modulation coefficients, your modulation weights in that sense. Okay, so what are modulation weights? Okay, so you of course also take C and you pass it through a layer so normalize it, and then you basically modulate it. By modulation, it just means simply multiply by alpha and add beta to it. So it's like a like a hyperparameter kind of thing, but it's not like hyperparameter which is set by a human. It's basically something that is learned using the Y itself, okay, and using a linear layer on top of Y. So you basically modulate the value of C. Similarly, you modulate the value of X on the right-hand side, and then you apply linear layer so as to essentially get a revised C and revised X. Now you further do some more normalizations on top of them so as to basically get a revised X and C or a modulated X and C. Okay. Now what you see here is very fancy. So you take the C, you take the X, and you do, this one basically is concatenation. So you do a concatenation of the two. So you basically get a concatenated vector out of it. Okay. And on that concatenated vector, you basically compute QKVs. Okay. So on that concatenated vector, you basically compute QKVs. Okay. Um, Now, once you get those QKVs are the basis of all self-attention. So you essentially do self-attention. So QK transpose to a softmax, and then you multiply by V. That basically gives you the revised vectors. You take your, again, since you started with a vector of size, size of C plus size of X, you'll basically get that same thing. So you take those first C components, pass them there, next, the last X components and pass them there. And then you do further such interesting operations. You element-wise multiply gamma, right? This multiplication is element-wise multiplication. Okay, and then you add the value of C. You add the value of C there. Okay. Again, you do not layer normalization, some modulation followed by a few dense layers, and that's basically your text output. Several times you have these residual connections. You have one residual connection here, you have another residual connection here, where you're basically making sure that your original C and your original X are also preserved. Of course, you have residual connections on the on the X side as well, on the image side as well. Okay. So that's how basically this MM-DiT architecture works. It's diffusion is based on a diffusion transformer, and it's a sequence of modulated attention and MLP layers basically. Okay. Now, how does Stable Diffusion 3 model with MM-DiT perform? Well, here is a comparison. So they tried to tune the model, and there are many hyperparameters, or some hyperparameters, interesting hyperparameters that you can use to tune. You could increase the number of latent channels. So as to remember, you're basically not operating on the original image, but operating on a latent image in that senses. So the latent image, of course, has lesser height and width, but you can all increase the depth so as to have higher accuracy. So they basically use a depth of 16 channels. Okay. The other thing is that you could, of course, train the entire network using standard image caption pairs. But what they observed is that standard image caption pairs lack diversity and they can be noisy as well. So therefore, they basically said that, hey, let us basically generate synthetic image caption pairs using CogVLM model. Okay. So overall, to train their model, they use 50% original and 50% synthetic captions. Finally, they train an 8 billion parameter model. Okay. As you observe, compared to other models like cross-DIT, DIT itself, or UVIT, MM-DIT essentially leads to lower validation loss, right? So a green one is MM-DIT and leads to lower validation loss as you increase the number of training steps. Also, as you increase the number of training steps, this is just validation loss, but as you increase the training steps, the test FID score is lower for the green guy, which is MM-DiT, and the clip score is higher for the green guy, which is basically MM-DiT. Compared to other baseline models, it is better. Okay. Finally, they also did human evaluation, where they asked humans 3 different questions. Which image. So basically, they compared models against MM-DiT, and they asked, hey, does MM-DiT generated image look more representative about the text which was provided, or let's say Pixar Alpha generated image looks more prompt following? Okay. They also evaluated on visual aesthetics. So given the prompt, which image is of higher quality and aesthetically more pleasing? Okay. Lastly, they evaluated on typography. So which images accurately displayed the text that was asked to be displayed in the caption? Okay. So more accurate spelling is preferred and so on. Okay. So across all aspects, they basically find that the win rate for MM-DiT is higher, compared to all of these models across all the 3 aspects, as you see. Sure, I mean, in some cases, basically this ideogram V1.0 model essentially is preferred slightly. But, if you look at the state-of-the-art models, otherwise, Pixar Alpha, Stable Diffusion XL, Stable Diffusion XL Turbo, compared to all of them, Stable Diffusion 3 seems to be much more prompt following aesthetically pleasing, generates aesthetically pleasing images and also accurately displays typography. In summary, in this video, I talked about the MM-DiT architecture and the Stable Diffusion 3 model, which is based on the MM-DiT architecture. It's the state-of-the-art in image generation. It is technically based on the rectified flow. Specifically, they observed that logic normal sampling for sampling more time steps in the middle it gives you better results. Right? Overall, it follows the MM-DiT architecture, which is a diffusion transform architecture, and it's an 8 billion parameter model. Okay, so that's it about the MM-DiT and Stable Diffusion. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage.